Hello everybody, welcome back to Real Analysis. We may be finishing up today, if not we'll come close. Before we do anything new, I want to review a couple of results from last time because we're going to be using those in some of our proofs today. So the first thing that we want to look at is the extreme value theorem. And it says, suppose that f of x is continuous on the closed interval AB, closed interval. Then f of x attains both an absolute maximum value and an absolute minimum value at some point on this closed interval. So that's the first thing that we want to remember. If we have a continuous function on a closed interval of finite length, but we're guaranteed that we have both an absolute maximum value and an absolute minimum value somewhere in that interval. Now, the next thing that we want to recall is that if f of x is differentiable on a closed interval AB, and it attains a relative maximum or a relative minimum at some point x naught, f of x naught, where x naught is in the open interval AB, then the derivative equals 0 at that point. So essentially, this is what we're looking at. Here's A, here's B, and at some point in this open interval, like right here, we have a relative maximum or a relative minimum, in this case a relative minimum, and the derivative is equal to 0. Notice we have the horizontal tangent here, so the derivative is equal to 0 at this point. So these two results we want to keep in mind because we're going to be using them on the first couple of theorems that we prove today. So let's get on with it. Okay, here are our conditions. On the closed interval AB, our f of x is continuous. And at the very least, on the open interval AB, f of x is differentiable. And we have one other condition. The value of f of x at the endpoints is equal. So f of a equals f of b. By the way, if we don't know, and we might not, this is the Greek letter psi, the p is silent. So if f of x is continuous on the closed interval AB and differentiable on the open interval, and if f of a and f of b are equal, in other words, f has the same value at the two endpoints, then somewhere in between a and b, there's a value of x such that the derivative at that point equals 0. And before we prove it, let's just draw a picture of what's going on. F of A and f of b are equal. So f of a and f of b lie on the same horizontal line. And somewhere in between, the theorem says that there's a value of x where the derivative is 0. In other words, we have a horizontal tangent. And clearly, just from the drawing, we do have a horizontal tangent somewhere between f of a and f of b. So if the function's differentiable, we're guaranteed that this happens. Now, just as a side note, there's nothing in this theorem that says that this point is unique. The theorem doesn't say that there's exactly one value of x, psi, where we have a horizontal tangent or where the derivative is 0. We may have more than one. But one thing's for sure, we have at least one. So, looking at another scenario, here's f of a and f of b, they're equal. So a, f of a, and here's b, f of b. The graph could do something like this. And so here we have a relative minimum. And over here we have a relative maximum. I better call that psi 2. And at each point, the derivative is 0. We have a horizontal tangent. So in this case, we have more than one point psi where the derivative is 0. In this case, we have two different x values where the derivative is 0. And that's permissible. The only thing that Rolle's theorem says is that under these conditions, continuous and differentiable, and with the endpoints A and B having a common value of f of x, under these conditions, there's at least one value of x in that interval where the derivative is 0. There could be more. There don't have to be more, but there could be more. But there's got to be at least one. So that's what Rolle's theorem is telling us. So we let the hypotheses be given. So here's where we apply the extreme value theorem. Our function is continuous on the closed interval AB, and that itself is enough to guarantee by the extreme value theorem that f of x attains both an absolute maximum value and an absolute minimum value on this interval. So we'll consider two cases. So f of x attains its absolute maximum value at one of the endpoints, and it attains its absolute minimum value at one of the endpoints. But now look at part of our hypothesis. F of A and f of B are equal. So let's see. Let's see. Do I really need to do this? Maybe not. I'm going to make too much out of this if I'm not careful. F of A and f of B are equal. And so that means the absolute minimum value and absolute maximum value have to be the same. Now, by definition of absolute max and min values, this means that the absolute min value is less than or equal to f of x, which is less than or equal to the absolute max value for all x in the interval AB. But f of A, and I'm just picking, I have a choice here. I can say f of A or I can say f of B. So randomly I'll pick f of A. F of A is the absolute minimum value, but it's also the absolute maximum value. So that's pretty significant. So for all x in AB, f of x is sandwiched in between f of a and f of a. Well, how is that possible? So f of x is a constant, where that constant is f of a. Now let's see. I guess this is where I stop and step back and try to remind myself, what was it that I was trying to prove? Under the hypotheses given, I was trying to prove that at some value of x in between a and b, the derivative is 0. Well, f of x is a constant, so its derivative is 0. Now, I think our hypothesis said we're not sure that f prime is differentiable at the endpoints, but it's differentiable in this open interval. So the derivative is 0 at each point in the open interval AB. So for any value of psi in the interval AB, the derivative is 0. So that's case 1. Remember, case 1 was that both the absolute maximum value and the absolute minimum value are attained at the endpoints. So case 2 is the negation of that. Either the absolute maximum value or the absolute minimum value It's a little known fact that in the old days when people knew how to spell, the word attained, past tense, had an E and a D at the end. Now, at least one of these, the absolute maximum or the absolute minimum value, has to be attained in the open interval AB. And if that's the case, the point psi f of psi is either a relative maximum or a relative minimum. Now let's see, where does that leave us? See, our previous theorem, one of the ones that we reviewed before we did this proof, said that if f of x is differentiable on an open interval, and we have a relative maximum or minimum in that open interval, then the derivative has to be 0 at that point. And that's what we wanted to prove. At some point in the interior of that interval, the derivative is 0. Well, let's see, do I really want that? I guess so. Let's see. So far, these look like the hypotheses for Rolle's theorem. And in fact, they are. The only hypothesis for Rolle's theorem that we're going to leave out here is the hypothesis where f of a and f of b are equal. For the mean value theorem, we do not assume that f of x has a common value at the endpoints. F of a and f of b can be different. Instead of f prime of psi equaling 0, f prime is going to equal the slope of the line that connects the points a f of a and b f of b. And we'll draw a picture of this in just a second to illustrate this. We are not going to prove this theorem now. We'll draw some pictures on the board to give us some intuition as far as what this says, but we won't prove this theorem right now. And the reason we won't prove this theorem right now is because this is one of our final exam questions. Now, I'm not completely heartless. I will give you some good hints on how to prove this, but this will be one of the things that you prove on the final exam. So let's draw a picture of what's going on here. Let's draw the graph of y equals f of x. And here's a, and here's a f of a. And over here, here's b. And here's the point b f of b. And the function f of x just sort of meanders around a little bit. So let's say that's what the graph looks like. The mean value theorem says that somewhere between a and b, there's some x value psi where the derivative equals this thing. And what we want to do is recognize what this thing is. This is the slope of a line that connects the point a f of a and b f of b. See that? y2 minus y1. See, y2 minus y1 over x2 minus x1. x2 minus x1. This is just the slope of the line that connects the points a f of a and b f of b. So for the sake of intuition, let's draw that line. Oh my goodness. So this line that joins points AF of A and BF of B has this as a slope. The mean value theorem says that somewhere between A and B there's this x value psi where the derivative equals this slope. But think about it. What is f prime evaluated at psi? Isn't the derivative the slope at x equals psi? So the theorem is saying that somewhere between A and B, we're going to have a tangent that has exactly the same slope as this line. So let's see. Here's a good candidate. Yeah, that looks good. They're parallel. They have the same slope. So here's the point psi, f of psi, and the slope of this line is f prime of psi. And the slope of this line is clearly the same as the slope of that line. So they have the same slope. F prime equals this thing. F prime of psi equals this thing. Now remember when we proved Rolle's theorem that we said that psi was not necessarily unique? Well, the same is true in the mean value theorem. Psi is not necessarily unique here. As a matter of fact, let me call this psi sub 2. Because we'll notice that there are other values of x in this interval where the slope of the tangent is the same as the slope of this line. For example, what about right here? Yeah, those two lines are parallel. So, right there, f prime of psi 3 is equal to this mess as well. And right here, same thing. Same thing. This tangent is parallel to that line. So we'll call this psi 1. So in this example, there are actually 3 different x values, psi 1, psi 2, psi 3, where the derivatives at these 3 points are equal to the slope that connects the endpoints of this graph on AD. So that's a visual demonstration of what we're looking at. We are not going to prove the mean value theorem. That's one of your final exam exercises. But we will proceed throughout the rest of this lecture as if we have proved this. in this discussion, I am going to be using capital F's and lowercase f's, and I am not using the two indiscriminately and whimsically. I will be making an intentional distinction between capital F and lowercase f. So essentially, an antiderivative is the function that we have to compute the derivative of to get little f of x. The derivative of each of these functions is 3x squared. So clearly, the antiderivative of a function is not unique. All of these functions, f of x, capital F of x, are antiderivatives of little f of x. So the antiderivative of a function is not unique. As a matter of fact, there are infinitely many of them that we can generate by taking the non-constant part of the function and just throwing on different constants each time. Now, is it necessarily true, as it appears in this case, that all antiderivatives of a function, and I beg your pardon, let me make that an equal sign. Is it true that all antiderivatives of a function differ from one another by a constant? The answer is yes. And we will establish that in a bit. These three bars may be thought of as an equal sign with emphasis. Literally, it's translated identically equal to. So in other words, this is an identity. It's true for all values of x. Plug any value of x in here, you get 0. That's what that means. So f prime of x is 0 for all values of x on an interval a, b. So if the derivative of a function is 0 for all values of x, then that function is equal to some constant. Let's see, how would we prove this? We don't have to. No, let me take that back. I don't have to. You will. This is going to be one of your final exam problems. And I am not going to be heartless about it. I will give you some hints to get through this. And we will proceed from here under the assumption that we know that this is true. In this lecture, we will proceed as if we know that this is true and as if we have proved this. But this will be one of our final exam questions. How do I want to save this? Okay, that's what I thought. Said differently, two distinct antiderivatives, although they don't have to be distinct. So any two antiderivatives of little f of x differ from one another by a constant. And we won't prove that here. That's one of our final exam questions. The next theorem, I really wasn't planning on giving this as a final exam question, but it's not hard. So maybe this will be a good final exam question also. So the general antiderivative of any constant k is that constant k times x plus an arbitrary constant c of integration. And there we have the power rule for antiderivatives. And it works for all exponents n except -1. Do I want to use k? I guess I do. The antiderivative of a constant times a function equals the constant times the antiderivative of the function. Okay. These, I guess, you'll prove on the final exam also. They're not hard. And I may give you a hint. Now let's move on to definite integrals. Now what this partition does is it partitions the interval from A to B into subintervals, n subintervals. And let's see, what do the n subintervals look like? X0 to X1, X1 to X2, X2 to X3, and by the way, X0 is A, and Xn is B. So this partitions the interval from A to B into n subintervals, and right now we're not requiring that the subintervals have to be of the same length. By the way, I should not have erased that, but we said delta x sub I is x sub I minus x sub I minus 1. So let's see. This is delta x sub 1, the length of the first interval. Delta x sub 2, the length of the second interval, dot, dot, dot. Delta x sub n, the length of the nth subinterval, and so forth. Now take that and look at it for a little bit. I want to give a graphic interpretation of this. So take a minute or two to look at it. And then I'm going to draw a graph and I'm going to create a Riemann sum based on that graph. Okay, here's my partition. Nothing great. And this is A equals x naught, x1, x2, x, well, let's see. I better go dot, dot, dot. And xn minus 1, and then b equals xn. And in each of these intervals, we pick a point, psi sub I. So in the first interval, pick a point, psi sub 1. In the second interval, pick a point, call it psi sub 2. And another point, and another point, and then another point in the last interval, psi sub n. Okay. Now note in our definition of Riemann sum, well, you know what? I guess I'll make this the ith subinterval. In our definition of Riemann sum, we had f of psi sub I delta x sub I. So let's see. There's delta x sub I. Here's delta x sub n. Let's note what this thing really is. Let me inscribe a rectangle. over the ith subinterval and notice that delta x sub I is the width of this rectangle. And let's see, what's this distance here? It's the difference of the y-coordinates. Here the y-coordinate is f of psi sub I. Here the y-coordinate, since it's on the x-axis, is 0. So the difference of the y-coordinates is f of psi sub I minus 0. The distance is just f evaluated at psi sub I. That's the height of the ith rectangle. Now guess what? If we constructed a rectangle over the ith subinterval, we're probably going to construct a rectangle over all the other subintervals too. If that's what you're thinking, you're right. So here's another rectangle. Here's our Riemann sum. And for each value of the index I, what we're adding to the Riemann sum is the area of the ith rectangle for I equal 1 to n. And one thing that we'll notice, perhaps for future reference, is that the area bounded by the graph of f of x in the x-axis from x equal a to x equal b is very well approximated by the sums of the areas of these rectangles. I'm assuming now that f of x is non-negative. The graph of f of x lies above the x-axis. And if f of x is non-negative, its graph lies above the x-axis as we've depicted it here, then very clearly the area bounded between the graph of f of x and the x-axis between x equal a and x equal b, that area is very well approximated by the sum of the areas of these rectangles. And that's something that we do want to note for future reference. Something else that I might want to introduce, and this is mainly for theoretical purposes only. For theoretical purposes only, in this example, or in this illustration, I very randomly and whimsically chose the values of psi1, psi2, so forth. The only restriction was that psi sub I, whatever it was, had to be in the ith subinterval. Psi sub 1 had to be in the first subinterval, psi sub 2 had to be in the second subinterval. Other than that, the values of psi1, psi2, psi3, and so forth were very randomly and whimsically selected. Now, we can create Riemann sums in which our selection of psi sub I is much more deliberate, and the selection is done according to specified criteria specified in advance. So let me do that. And this is absolutely nonsense. I meant what I said, but I didn't say what I meant. Oh, crud. Now notice that since f is continuous and each of these subintervals is closed, on each subinterval f of x attains an absolute minimum value. And wherever that absolute minimum value occurs, we let that x value be psi sub I. So in each case, this is the smallest value of f of x in each subinterval. And now let me describe the analogous counterpart. See, I better use something other than psi sub I, alpha sub I. We'll use a capital S sub n for this. Now, just to illustrate, I'm going to draw a picture of each of these. And remember, this is pretty much for theoretical purposes that we introduce the concept of an upper Riemann sum and a lower Riemann sum. And we'll have some partition, A equal x naught, x1, x2, x3, what, blah, 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 x4. b equals x5. Okay. Now, in each subinterval, psi sub I is going to be the point at which f of x attains its smallest value. And in the first subinterval, it looks like f of x is its smallest right here. So I'm going to make that psi sub 1. And this is going to be my height for the first rectangle. Now the second subinterval, I'm going to let psi sub 2 be the smallest value of f of x in this subinterval. And it looks like f of x attains its smallest value right there at this endpoint. So this is going to be my psi sub 2. And I guess I should label this point too. This is psi sub 1, f of psi sub 1. Okay, the third subinterval, it looks like f of x attains its smallest value right there. So I'll call this psi sub 3. And that's going to be the height of my third rectangle. Psi sub 3, f of psi sub 3. Guess what? On the fourth interval, this is where the function attains its smallest value. So this point is psi sub 4, f of psi sub 4. And then on the last subinterval, it looks like this is where the function attains its smallest value. So call that psi sub 4, no, psi sub 5. It's in the fifth subinterval. Psi sub 5, f of psi sub 5. And this is what our lower Riemann sum looks like. Well, let's see. How well does the sum of the areas of these rectangles approximate the area bounded between the graph and the x-axis? I guess it's not a bad approximation. But if we add up the areas of all of these rectangles, we're definitely going to get something that's less than the area bounded by the graph and the x-axis. So we'll note for future reference that the value of the lower Riemann sum, which is the sum of the areas of these rectangles, the value of the lower Riemann sum is going to be less than or equal to the area underneath the curve and above the x-axis. And also for future reference, we should note something else. Using this same partition, if we have any other Riemann sum using this same partition, let's see what happens. Let's say that's our f of x of 1 there. And let's say this is our f of x of 2 here. And that's f of x of 3 there. And this is f of x of 4 here. And this is f of x of 5 here. Well, you know what? These rectangles have more area than the rectangles that we used for our lower Riemann sum. So if we have any other Riemann sum based on this same partition, the value of that Riemann sum is going to be greater than or equal to the value of the lower Riemann sum. Now let's do an upper Riemann sum, just for the sake of comparison. And I'll try to redraw the graph pretty much the same way. So here's a equals x of naught, and here's x1, x2, and x3, x4, and x5, which equals b. Okay. The same function, the same partition. But now, in each subinterval, I want to pick as my x value psi the point at which f of x assumes its largest value. And I think that happens right here in the first subinterval. So here's my psi sub 1, and psi sub 1, f of psi sub 1. In the second subinterval, I'll say this is psi sub 2. Let's say this is where f of x attains its largest value in the second subinterval. So here's psi sub 2. And in the third subinterval, clearly, right here is where f of x attains its largest value. So this is psi 3, f of psi 3. And in the fourth subinterval, largest value of f of x occurs right here. So this is psi sub 4. And then, oops, and let me label that psi sub 4, f of psi sub 4. And largest value in the fifth subinterval, let's say it's right there, psi sub 5, f of psi sub 5. And so here's our upper Riemann sum, capital S. Oh, and oh crud. I was supposed to call these alphas, wasn't I? I'm sorry, use your imagination. I don't think I can redo all of this. But notice something here. The upper Riemann sum is the sum of the areas of all of these rectangles. And clearly, the sum of the areas of these rectangles is greater than or equal to the area bounded by the graph of the function in the x-axis. So the upper Riemann sum is always going to be greater than or equal to the area bounded by the graph of f of x in the x-axis. And think about this. Suppose that I had any other Riemann sum. Let's say here's my f of x1, or f of whatever, and here's my f of whatever 2, and here's my f of whatever, and so on and so forth. If I have any other Riemann sum, the areas of these rectangles are going to be less than or equal to the areas of the rectangles that I have in my upper Riemann sum. So not only is the upper Riemann sum greater than or equal to the area bounded by the graph of f of x in the x-axis, the upper Riemann sum is also greater than or equal to the value of any other Riemann sum that we can create using this same partition. And that's something that we want to remember. And after I erase this, I am going to beat those points to death a little bit further. Can we read that? I sure hope we can. Let me make it a little bit larger. So capital A, that's the area bounded by the graph of f of x and the x-axis between x equal A and x equal B. The lower Riemann sum is always going to be less than or equal to that area. And the upper Riemann sum is always going to be greater than or equal to that area. Tell you what, let me just call this regular S sub n. Not a fancy S, just a regular S. Any other Riemann sum that we create using this same partition is going to be greater than or equal to the lower Riemann sum and less than or equal to the upper Riemann sum. So the lower and upper Riemann sums form bounds for the values of all Riemann sums, and they form a bound upper and lower for the area bounded by the graph in the x-axis. Okay. So this is any partition of order n of the interval AB. So essentially the norm of delta I, denoted this way, is just the largest of the values of delta x of I from I equal 1 to n. So essentially what we're saying is this, and note some consequences of what's going on here. If the length of the largest subinterval is going to 0, and the endpoints of the overall interval remain the same, well, I guess the only way that could happen is if the number of subintervals increases. So as the length of the largest subinterval goes to 0, that also means that n, the number of subintervals, has to go to infinity. Notice here we talk about the common limit of all Riemann sums. So essentially, we're supposed to get the same value regardless of what partition we choose and regardless of our choice of psi sub I for each interval. And if that's the case, if we get the same value, no matter what partition we choose, no matter how we choose our psi sub i's in each subinterval, then the integral of f of x, the definite integral of f of x, is said to exist, and it equals the common limit of these Riemann sums. And if all Riemann sums have the same limit as delta x goes to 0, we say that the function is Riemann integrable over that interval. If the function is Riemann integrable, then it doesn't matter what partition we use. So why don't we just use the partition that's going to make things easiest for us? We'll just take the interval from A to B and divide it into n subintervals of equal length. Each of those subintervals will have length delta x. And that's typically what we do. So all the subintervals have the same length, delta x, and x sub I can be any point we want in the I subinterval. In the final analysis, it won't make a difference. Notice this again. If delta x, the length of each subinterval, is going to 0, then the number of subintervals is also going to infinity. I want to beat this point to death because I really don't think this gets enough attention. Whenever we have an integral from a to b, and our variable is x, we might think of this as x equals a and x equals b. The lower and upper limits, respectively, are the endpoints of the interval that we partitioned into subintervals. So when we see an integral like this, from x equal a to x equal b, know that this integral originally started out as a partitioning of the interval from a to b on the x-axis, and a and b were the endpoints. That's very helpful to remember. And another remark. If our function is non-negative, in other words, the graph of that function lies above the x-axis, then the integral of f of x from a to b is the area bounded by the graph of x, bounded by the graph of f of x and the x-axis. Between x equal a and x equal b. So it's important for us to have that understanding. And maybe I can make one more comment about this. think I need to tweak this just a little bit. The algebraic sum of the areas of Okay, I think that's a little bit more accurate. The definite integral from a to b, and here we're not assuming that f is non-negative. F of x can be positive, it can be negative, it can be, above the x-axis, then down below the x-axis. The definite integral is the algebraic sum of the areas of the bounded regions above and below the x-axis, treating the areas of the bounded regions above the x-axis as positive, and the areas of the bounded regions below the x-axis as negative. Now, I think I have more to say. This is the end of this lecture, but I think I will have another lecture to follow up. So stay tuned, please.